Rohit ji, Dr. Dan has joined. Please make him co-host. Also, Saida Nehel also. And Dr. Ankur. Dr. Dan, are you able to hear me?
I can. Can you hear me?
Yeah, yes. Would you like to share your presentation?
Of course. I'll just put my camera on if you can see me.
Yes,
That's
yes.
wonderful. That's great. In which case, I will share my screen.
Yeah, please. Rohit, please help Dr. Dan.
Okay. Hello, sir. Dr. Dan, yeah,
I think it's coming up.
yes, it's loading. Yeah, it's there.
Okay.
Thank you, sir.
Uh,
Okay. So I'm just going to check whether these captions, I don't think they move when I talk, so that's that's something. Maybe they will go. That's wonderful. Shall I make a start then?
yeah, Saida, please start the session.
Yeah, ma'am,
Brilliant.
am
Thank you
I
very much.
audible?
Yes, yes, all good to go. Please start.
A very good evening to everyone present here. Respected dignitaries, esteemed speaker of the day, honorable course director, faculty members, and my dear participants joining us from the different parts of the country and abroad. Welcome to this special session of the Krishi Navyug, a 3-month training cum internship program organized by the Agriculture Valley Research Foundation, New Delhi. I, Nahal Zahra, Technical Secretary to the founder of AWRF, feel highly honored to host and coordinate today's session on this remarkable 52nd day of the Krishi Navyu, a journey that continues to build knowledge, innovation, and capacity in the field of agriculture and environmental sciences. Today's session is especially significant as we are privileged to be joined by the eminent personality from the field of soil science and environmental research. It is my great honor to introduce our distinguished speaker for today's session, Dr. Dan Evans, a senior lecturer in the Soil Science Department at Cranfield University, United Kingdom. Dr. Evans is a celebrated soil scientist whose research focuses on the hidden processes that occur as rock transforms into soil, integrating geology, chemistry, and microbiology. He holds the prestigious UKRI Future Leaders Fellowship, where his groundwork work explores the role of soil parent materials in the carbon cycle and their potential in climate change mitigation and net zero pathways. His research investigates how carbon can be stored deep within the soil systems and what governs its long term stability and release. Dr. Evans has received international recognition, including the Outstanding Contribution to Soil Science Award at the World Congress of Soil Science in 2022 and the Arne Richter's Medal for Outstanding Early Career Geoscience in 2024. He is also actively engaged in policy and leadership roles, serving as a co-chair of a national greenhouse gas removal network, director of the UK Soil Scientist Apprenticeship Programme, and deputy president at the Soil Science at the European Geosciences Union. Beyond academia, he is deeply committed to public engagement through talks, media, and innovative initiatives like the Talking Soils Bench. We are truly honored to have him with us. Without any further delay, I now kindly request our esteemed speaker, Dr. Dan Evans, to please kindly take over this session and share his valuable insights with us. Sir, if you would, the virtual platform is all yours now. Thank you.
Thank you very much. And it's a great pleasure and honor for me to be here with you all today. Thank you so much for the invitation. I am currently at the World Congress of Soil Science 2026, so 4 years on from our meeting in Scotland in 2022. And it's 8:30 in the evening and it's been a long day, so I apologize. I am not at my sharpest, but we'll have a good session, I think. And think because of the nature of the equipment I have, I'll be very happy to take questions at the end of the presentation. So with that, I would like to kind of introduce the title, which is in a sense digging into the future. For me, this is really relevant because my work has just been introduced is around the formation of new soils. We think of soils that have been around for hundreds or thousands, sometimes tens of thousands of years. But actually, where my work sits is at the transition zone between often bedrock or parent material and soil. And that's where the new soil is forming all of the time. And to be honest, it's an underexplored zone in soil science and in wider geosciences. So there's a lot of things we don't actually really know or understand about this particular transition zone. And that's where some of my work and those of my colleagues will come in. So to start off with, soil is really central. I don't need to say just how important soils are. Soils are a valued material, and they particularly link up to 5 specific, what I call capitals of natural, social, human, built, and financial. And these prisms or aspects of our lives, each one of us, and indeed everyone living here on Earth, is in some way dependent on healthy, sustainable, and resilient natural resources, integrated social and human resources, really quite essential built infrastructure, and of course, money. Makes the world go round, apparently. Financially, soils have a large part to play in keeping all of these capitals not just healthy, but enhanced. And we can link up each of these 5 capitals to the Sustainable Development Goals, which as we approach the end of the decade, we will need to reflect and think about what those development goals might look like after 2030, the year in which they're meant to be achieved. So we have obviously lots of work to do, and of course it's courses and programs that you're on at the moment, and many programs around the world that are feeding into building knowledge and understanding around soils, but recognizing that soils as a material are really valuable for all of these development goals. So one of the things that I had a great honor to be part of some 2 or 3 years ago now was the inaugural article for a brand new journal called The Innovation Geoscience. And this was one of the first articles that was published. It was a very, very large international team, some 60 authors or so from about 100 or so countries, came together to think about how soils are part of our strategy for climate change. And the article went obviously broader than just soils, but notice how so many of these aspects of mitigating climate are soil related, directly and indirectly. So think about those climate change drivers, how we might use soils to help create new bioenergy fuels, how we obviously need to manage waste resources across the world, how indeed soils are very part of the way in which we afforest landscapes. And they're really quite key in mitigating the effects of climate change from land use change. So climate change drivers are very, very important. And on the top right here, you can see climate change effects. And we know that climate change has an impact on so many different types of phenomena. Climate change expresses itself through the soil in terms of a rising global temperatures. That will obviously affect soil biodiversity. It could also affect precipitation patterns, and the soils themselves are affected by those precipitation patterns. Heavier, rainier seasons will cause more flooding. And of course, we know that in summers, many soils around the world are becoming more desertified. Climate change mitigation measures like sustainable agriculture, carbon capture and storage, to some extent how we might improve irrigation efficiency, how we can just restore degraded ecosystems, how we can get life back into those desertified environments, how we can diversify crops, how we might think about agroforestry. All of these aspects rely on good, healthy, sustainable and resilient soils. And soils, we tend to walk on them on a daily basis. Many of us will work with them. And it's important at this stage to recognize that soils, just like the houses that we live in, have multiple layers, and those different layers are connected by different pathways, different channels that provide, in a sense, the ability for nutrients and water, for indeed carbon, to transport from the very surface down into those lower levels. And I use this analogy because it's important that we understand that we don't just need to manage the surface. We don't just need to manage, in a sense, the rooftop of our house. We have to manage all of those horizons. It might be quite obvious to say that, but the majority of work in soil science, indeed the majority of soil management, really only focuses on that surface layer, the top level of our house, rather than focusing on the layers below that top layer. And indeed, the work I do is very much at the basement and ground level of our house, in the sense that soils form from the parent material, the foundations of our soil profiles. And it's that framework that provides stability. Agriculture, whether you are thinking about arable or indeed livestock, all agriculture relies on soil. But the world of agriculture would be very different if we only had the top 30 centimeters of soil. Indeed, there's many parts of the world where there are only 30 centimeters of soil. And in those parts of the world, crops are suffering, and plants often find they don't have enough space to develop root systems and acquire the important resources that they need to grow. So the depth of soil, the thickness of soil is very important. It does raise a question, though, about where soils end, where does parent materials start? It's a very simple question: how deep is your soil? But many people find it difficult to quantify the thickness of their soil, because finding the difference between a soil and a parent material is easier said than done. In the field, you are confronted by a range of different horizons, and it's not as clear cut where that horizon between soil and the bedrock is. And this, to some extent, has been a problem for over 100 years. This is an article that was published way before I was born, in 1924, so over 100 years ago. And in this particular article, P. Brown, a soil scientist from the US, asked, where shall the boundary line between two soil types be placed? And what he was talking about there was the lines between different soil types across a field. Many of us will work with fields that have more than one soil type, and finding where that boundary is quite difficult. But we can also think about this in the sense of, where does the soil start and where does the parent material end? And we still have that debate even to this day within soil science. We are still 100 years on debating whether a material is regolith or weathered rock or soil. We ask questions like, what does soil actually mean? How do we define soil? Now, I'm talking tonight to a course which is focused on the big questions, the big challenges of soils. And before we go a minute further, we really should define what soils are. Otherwise, how can we talk about them? And worse still, how can we manage them? So we should think about soil thickness, because thickness of the soil affects many different variables that we rely on for sustainable agriculture. So the thickness of the soil will affect the storage of nutrients and the ability for soil profile to retain water. And because of that, it will also affect the diversity and indeed actually the abundance of microorganisms within a soil. And of course, the big topic, and one which I work on, is the storage of carbon. A thicker soil is going to be able to hold more carbon than a soil which is much thinner. And of course, for soils which are planted, the depth of soil has a bearing on the depth of plant roots and how deep those plant roots can go to acquire those nutrients and that water and the carbon that they need. But the question, of course, is how do we determine the soil thickness? And this is the question that I was asked when I did my PhD many years ago. At the end of 4 hours of talking about soils, the last question I ever really had was, where does the bedrock stop? Where does the soil start? And how do we define the thickness of a soil? Well, I mentioned, of course, that on upper layers. And this is a survey that we did a few years ago now by Kimber Morland and myself. Kimber Morland is a soil scientist at Stanford University in the United States, one of my key collaborators. And we did a survey about the depths to which the soils community sample. And you can see here that there is a kind of median depth that they sample. It's around 40 centimeters or 0.4 meters. This was around 116 survey participants. And of course, some did measure further, and you can see here where some soil scientists are surveying down to a meter, some are even reaching down to tens of meters, and to some extent even 50 meters. And of course, there are soils out there that are that thick. Some of the soils I've worked on in Brazil, for instance, are 45, 50 meters thick. But on the whole, the majority of soil scientists measure the top 40 centimeters. Well, if you compare that with some of the average soil thicknesses around the world, so a couple of kind of estimates here from the early noughties, Badgers and Hill basically said that we're looking at about a meter. David Montgomery in 2007 suggested that the median soil depth was between 1 and just below 3 meters. And indeed, for UK soils, where I'm based, our soils are actually between 75 or so and about 1.5 meters. So basically, the take-home message is that we know that soils are deep, but we're not surveying them down to those depths. And one of the problems with this is that when we get down into those depths, it gets very subjective. There are many different ways of dividing or categorizing the horizons in a soil profile. There are geophysical techniques which are emerging, seismometers which are used principally to track earthquakes, but we can use that same kind of technology to infer the depth of a soil. But I think one of the problems is that we often rely on these very physical, property-based approaches. We use geophysical techniques to get a sense of where the bedrock is, but some bedrock can be like a soil in that it can hold water, it can hold carbon, it can hold microorganisms. So that weathered rock, although it's a different kind of layer, is still really part of the soil profile, and it functions in many ways like a soil. So a piece of my work has been just how fast does soil form from bedrock? And it's a question that many don't ask because it's just conceived to be quite slow. But the rates of soil formation govern the speed at which soils form, and we can use these data to assess land degradation and erosion, and evaluates indeed the success or the effectiveness of soil conservation schemes. And of course, the rates at which soils form actually control many of the key supply rates for nutrients. So we think of phosphorus, for example, which is critical for plant growth. That has a large bearing on the ability for plants to grow successfully, sustainably and resilient. But that supply of phosphorus partly is dependent on the rates of soil formation. Many billions of years ago, 2.5 billions of years, we didn't have any soil. There was very little soil, nothing that we can really call soil on the planet. And the emergence of soil was a result of cyanobacteria that colonized the bare rock of our landscapes. And it was a very slow process, but that cyanobacteria released organic acids that geochemically and biochemically weathered the rock. So these bacteria basically turned rock into soil, and in doing so, actually put oxygen into our atmosphere as a result. And if it wasn't for those cyanobacteria creating soil on rock, we may not have oxygen in the atmosphere for us to breathe today. Soil formation over many billions of years has been like that, slow and steady, and often a small process that over a long period of time causes great change. For instance, in this particular example, a boulder is split open by the action of water freezing and expanding and creating a gap into which more water can reside and expand and contract, again to make that boulder essentially break into smaller and smaller chunks, hydrological weathering. And we also find lots of biological weathering. Anywhere you go around the world, you'll see lichens and mosses, cryptogamic ground covers, which are essentially eating into the rock. And when those lichens have created a sufficient depth of soil, then come the grasses, the herbs, the larger vegetation, until you get trees whereby the roots themselves are creating new gaps. And you can see this here in this root, which is causing a new piece of soil to form in this sandstone bedrock. Sandstone, fairly friable, it's fairly weatherable. These roots don't have any work to do really. All they need to do is grow and split that bedrock open and create soil. But weathered material doesn't necessarily make a soil. We know that there's more to soil formation than rock weathering. So there's a bit of a two-chapter story. The first chapter is the rock weathering down into more finer, to some extent, granular material. And then there's the constructive process of building good, sustainable, healthy soil structure, the key to a healthy soil. And there's been some work on this by colleagues of mine over in Germany and across Europe, which is essentially looking at the life scale, the lifeline, if you like, of weeks and months, how these small particles coalesce to form microaggregates bonded together by minerals, by organic compounds, to some extent by plant roots. And these aggregates create larger and larger aggregates. So they create macro aggregates. And these macro aggregates are glued together with plant roots, with organic compounds, with substances released by organisms, by bacteria. They're glued together. And these form really stable macro aggregates that, when you sieve the soil, essentially are resting on top of the sieve rather than going through the holes. Soil structure is not static though. And it's a bit like playing Jenga. If many of you have played Jenga, where you take a brick out and hopefully the whole thing doesn't fall. Soil structure is a bit like that. It's continuously being disturbed, being reorganized, reconstituted. The particles of soil change shape, and the pore spaces in between the particles are always dynamic. Here you can see particles in brown, and these blue dots here are the water between particles, which will obviously change their orientation when these start to move and become larger aggregates. And soils can have some resilience, but at the end of the day, they can fail and the whole Jenga can fall down. And it's particularly the case when we plough the land that we disrupt this soil structure and cause those macro aggregates to disintegrate into those micro aggregates and to some extent back to individual particles of sand, silt, and clay. And this is a problem because in many parts of the world, the reduction of healthy soil structure can lead to the erosion of soil. And this is close to where I live in the UK. You can see under the soil profile here is chalk. That's the parent material. And the soil has eroded away, exposing bare chalk at the soil surface. You can even see that the farmer has been ploughing up and down the land, up and down this slope. And you can see even in the tractor wheelings, the exposure of chalk. And typically we would recommend that on steep slopes like this, that the farmer doesn't plough up and down, but sometimes it can't be helped. Sometimes for safety reasons, the tractor or farm machinery has to go up and down rather than across. But of course, this doesn't help with the mitigation of soil erosion. And of course, there's been many claims in the media around there's 60 years of farming around the world. What if the world soils run out? To some extent, even where I live at the moment in the UK, there's a claim that there are 100 harvests left. And all these are only media claims. And if you go to the Food and Agriculture Organization of the United Nations, the FAO, Status of the World Soil Resources Report, you'll see that these claims are not made, but the pressures of erosion are very evident in the data. So these media claims are not matched with evidence, but erosion is still a big issue. And we can see that when we look at maps of erosion. This particular one was done for the European Union. At the time, the UK was part of the European Union. You can see the erosion loss rates are particularly high around the southern area of the Mediterranean. And you can see that these areas are areas where soils are eroding rapidly and exposing parent material from underneath, just like my example here of the chalk underneath the farm. And some parts of the world, the rates are very slow, but the problem with a map like this is that it only shows you the erosion rates. It doesn't necessarily show how fast the soils are forming. Because of course, a soil is very much like a bank account. You have outgoings and you have incomings. And this map really only shows the outgoings. We don't have the same map for the new soil that's being created. So you look at this and you think that the erosion down in the Mediterranean is particularly severe. But it could be the case that formation rates of soil are also quite high down in these areas. And so you might then conclude that the erosion rates are cancelled out by the generation of new soil. In other words, the soil thickness remains the same. Whereas further up, where perhaps the erosion rates aren't so bad, these erosion rates might still outpace the rates of soil formation. And as a result, we have instances of soil thinning down to bedrock. The problem is we have very little data. of soil formation. Only a couple of hundred rates have been measured globally, and only about 30 rates for soils which are over a metre deep. Many of our soil formation rate measurements have been done on mountains and catchments that are not managed by agriculture. Very few rates exist for soils managed under arable agriculture. In fact, the rates that we do have, I've measured in the last 5 or 6 years. One of the things I did some years ago now was to compare the rates of erosion with the rates of soil formation. So basically what I did is I went round to a large data set and built up a global map of where erosion data had been collected. We had over 200 or 250 locations across 38 countries. And then we used a similar type of data set that I published previously on soil formation. And we did a bit of a mass balance model. So essentially we asked how long would the soil have left until bedrock was exposed based on these rates. And we compared this for different management types. And the key message is that for soils which were conventionally managed, and by this I mean that they are subject to no particular sustainable management, ploughing happens up and down a slope, there's no conservation action really taken to hold these soils in place. For this particular subset of the data, over 90% of the soils are thinning, they are eroding faster than they're forming, and about 16% had lifespans of less than a century, less than 100 years before the top of those soils were eroded. And interestingly, for soils which were managed with conservation practices, so they had cover crops, the agricultural practices left soil on the field rather than ploughed it away. That, for instance, we saw the use of organic amendments to hold soils together. Only 7% of the data had lifespans less than 100 years. Compare that with 16%, and nearly half of the lifespans exceeded thousands of years. So it goes to show that it can happen. We can't necessarily prevent erosion, because erosion, after all, is a natural phenomenon. It's been going on for billions of years, but we can slow erosion down, and at the very least, we can keep those rates of erosion smaller or slower than the rates of soil formation. We created a infographic at the Oxford University's Our World in Soil Data, Our World in Data, Our World in Soil Data. I'd wish it was about soil data, but it's about other types of data. But Our World in Data, you can see more information. There's also a YouTube video when I was looking a much younger man than I am today, less international travel back then. And I mentioned that we didn't have any rates under agricultural soils. I created the first rates for agricultural soils about 6 or so years ago. And albeit only about 20 or so rates compared to the larger global inventory. But notice how the soils under agriculture also allowed us to measure soil formation for soils over a metre thick. You can see that the majority of the soil formation rate inventory is for very, very shallow soils indeed. And we've communicated across the way, and in the introduction it was mentioned that I like to communicate my science to policy and indeed to wider society. We wrote a couple of things from this, and indeed this was part of the Welsh Government's soil policy evidence report that they used to generate policy. So very important that science is used for impact, and this is one of the reasons I like doing these kinds of talks for other things. And the question then I asked was, does the soil erode at a constant speed? And the answer really is no. Soils, when they erode, are affected by the erodibility of the soils, the susceptibility of those soils to erode. And that can be a factor of organic carbon. If you've got more organic carbon, it tends to be the case that erosion rates are slower, not exclusively. The texture of soil also is very important, the particle size distribution. In this particular modelling paper that we published a few years ago, we showed that soil profiles can accelerate and decelerate depending on the type of soil texture that you have in the subsoil. So these blue dots here that show an accelerating erosion trend over 500 years. So we're taking today as day zero and we're fast forwarding 500 years of erosion. The erosion not only happens, but it accelerates over time. The soil loss increases. And what you can see here is that these soils are silt loam over a loam subsoil. What we've found, though, is that some soils show a decelerating trend over this period. And this is because the type of soil below that silt loam is of a different texture. So it makes a difference knowing what the particle size distribution is down the soil profile, not just at the surface, if we think about erosion. So also what we found is that profiles that had decelerating erosion had increased stone cover and decreasing silt contents. And the profiles that we had acceleration in erosion rates tended to have more silty soils underneath the top. So if you've got a soil which has many stones in it and has increasing amounts of sand or clays, then its chances are that those soil erosion rates will decelerate over hundreds of years we're talking about here. But the profiles that have very silty soils will have an acceleration of erosion rate. And the question obviously is, well, so what? Why is this important? Well, it's important because it means it affects the soil thickness. We can understand the changes to soil thickness and how we can manage them. We can't necessarily change the stone content or the particle size underneath a soil profile. You can't just swap sand for silt because you don't want a sandy soil. So what can you do? Well, you can manage the surface and slow those erosion rates down, and hopefully with that you can allow the soil formation process to catch up with those high erosion rates. So yes, we can ask how fast does soil form, and that in a sense has been a lot of the work I've done in recent years. But the big question that I'm asking at the moment is actually what soil functions emerge at the bottom of the soil profile, because we tend to think that the top layers of the soil are all where the exciting stuff happens. Not the case. At the bottom of the soil profile, there's a really exciting number of processes happening. And what I want to quickly highlight here is just how the bottom layer of the soil holds carbon. So there's a vast range of research that shows ecosystem goods and functions, ecosystem goods and services taking place in the material below the soil, in the parent material, in the bedrock. So we've got colleagues who are looking at the plant use of water in bedrock, how forest vulnerability to drought actually is controlled by the bedrock as well as the soil. Colleagues of mine will be thinking about the biology in the bedrock. And this is an interesting study in the bottom right here, which I do recommend having a look at. There's a really nice edited lay summary to this paper as well, published some years ago now, but actually what they found was quite alarming. They found that more than half of the carbon dioxide produced by soil respiration is not returned to the atmosphere. So we think of microbes taking carbon and respiring CO2, and that CO2 goes into the atmosphere. What this particular study showed is that some, indeed more than half of the CO2 produced, actually was dissolved in the pore waters in the soil. And when you mix CO2 in water, it creates carbonic acid. And this carbonic acid, weak as it is, can be transported deeper and actually cause more weathering of that bedrock in places. So the CO2 acts as a kind of weathering agent for more soil formation in a strange kind of way. But one of the things that I'm interested in, and I'm doing a lot of work on my fellowship at the moment, is thinking about the storage of organic carbon. We know that soils are important carbon stores. We know that one of the big challenges that we face is increasing the amount of carbon stored in the soil. What we don't necessarily know is the extent to which the parent material underneath the soil holds carbon. How much more carbon can we get in that parent material? So I like to think, if I go back to the analogy of a house, that we've been trying to pack carbon into the house, and the house is full, it can't get any more carbon, and yet we're trying to put more organic carbon in. And then we open up the hatch underneath the floorboards of the soil, the floorboards of our house, and we can see a hidden vault which is empty. And this is the parent material, material that was once rock. It's forming into soil. Structurally speaking, geochemically speaking, this material is dynamic. It really is at the interface between the geological processes taking place in bedrock and the pedological processes taking place in soil. And some of the work we've done recently has shown that this layer can be a real game changer in terms of below ground carbon storage and storing carbon long term. So some of the questions I'm asking at the moment are: what factors affect the stocks, the ability for parent materials to store carbon and store it for a long time? We want the carbon to stay there because there's no point in us putting carbon there if it's going to leak out of the system. So are there particular mechanisms that help keep that carbon stable deep in the soil? Some of the other questions I'm asking are: at the surface, where we have desert environments or even very degraded landscapes, where the soil has been washed away and we have exposed bedrock, how can we make better use of lichens, fungi, mosses, cyanobacteria that started it all off for us those 2.5 billion years ago? How we can use these to introduce carbon into the structure of the rock itself. So we're using special X-ray CT scanners to peer non-destructively at a column of soil and to see how these, albeit quite small organisms, can create big changes in the soil. And of course, then we're looking at larger root systems. So for most roots, they will release organic compounds. And how do those organic compounds get into the parent material? Some of the work we're doing at the moment is looking at how roots can penetrate into rock by releasing organic compounds to help lubricate their way through the rock. And of course, by releasing those organic compounds, you're releasing carbon into the system. And the other question I'm asking is around rock-derived carbon. And I'll come on to that in just a second. But just want to show you some work that we've done that proves parent materials can hold organic carbon. So we did this piece of work for Great Britain some years ago now, but it shows that in parent materials, after the last ice age, tills, alluviums, some glacial fluvial deposits actually hold lots and lots of organic compound. a large amount of organic carbon, lots of organic carbon in these parent materials that we wouldn't normally survey at all. We wouldn't normally think of them as soils. Here they hold as much as 385 megatons of organic carbon. And work done by my colleague I mentioned earlier, Kimber Moreland and colleagues, this is in Environmental Research Letters, a really nice study showing that rock 10 meters below the soil had within it about 30% of the carbon stocks found in the total soil profile. So think of that. Top 10 meters of soil has organic compound, but a third of that profile's carbon stocks are found in weathered rock. So the carbon is making its way further down than we think. And we've done this in field sites. This is a really nice field site of mine because actually it has 3 different types of parent material within walking distance, about 100 or 200 meters away from each other: mudstones and siltstones, slates, sandstones, quite thin soils here. And what we did is we measured the carbon in the soil and, of course, in the weathered rock, the saprolite, as it's sometimes called. And this is a very basic kind of figure, but shows that we have very similar stocks in the parent material compared to the soil. So you can see here for this particular parent material, which I think was the siltstone, that the stocks of organic carbon in the parent material equate to the stocks that we typically find in the soil profile. Sometimes that's less obvious, but in this particular case, you can see that there is, although a large range of organic carbon, quite similar. So we think that what's happening here is that the roots are inputting biogenic, that is to say plant-derived carbon, into the parent material. So the big question then is, should we really incorporate this into our models, into our understanding of soil carbon? And if so, how would we do this? The other big question is, what happens to this carbon in the parent material when those materials form soils? We know that those parent materials will weather into soil. What happens to the carbon in those parent materials? Does it go back into the soil? And if so, how stable is it? The final thing I want to mention before I wrap up is the fact that some parent materials can also release carbon. What do I mean by that? Well, some bedrock contains rock-derived organic carbon. So many millions of years ago, marine organisms were decomposing on the seabeds, the ocean beds, and over time they were buried under sediment, and then they were what we call forced or pushed into rock, and that rock was then full of carbon, full of the carbon from those marine organisms. Now, on the seabed or the ocean bed, that's fine, but what happened over millions of years is that this rock then emerged by tectonic activity into mountain landscapes, such as the landscapes you can see here from Switzerland. And we call this particular carbon organic carbon from rock, petrogenic organic carbon, petro meaning rock, and genic from, so petrogenic organic carbon, or as I call it, OC petro, organic carbon from petrogenic sources. And one of the big questions we're asking at the moment is, when soils form from these types of bedrock, so shale is a really good example of this, where does the OC petro go? And we did a bit of a study in Switzerland a couple of years ago, where we have a glacier in the valley which is retreating because of warming. And in front of the glacier, you can see these sediments, which are essentially shale, which is grounded up into a granular structure. and this is full of organic carbon, but the OC Petro kind. No plants are here, no lichens or mosses are in front of the glacier. It's purely organic compound or organic carbon. And we went down the valley and we saw that over the space of 300, 400 meters, the vegetation increased. So we started seeing pioneer microbial communities, small dwarf vegetation, some thickening of the mineral soil. And then at the very further points down the valley, we saw established grasses and even some grazing. But what I wanted to show is that even here, where you don't see anything growing at all, just a few small pioneer communities, a couple of mosses and lichens, you had a respiration signal of CO2. So the question then is, how do those microorganisms survive enough to respire out CO2? What are they feeding on? Because there's no plants there. And the big hypothesis we have at the moment is that they're feeding on the OC Petro, the carbon which is in the rock itself. And this is a big deal because we don't at the moment include OC Petro into our carbon models. We even found that rates that we measured actually are an order of magnitude larger than some of the rates that have been previously measured using other techniques. So we have lots of carbon being released by these landscapes. And we've published last year a paper which explores some of the known unknowns of petrogenic organic carbon in soils. And if you're in an area which has shale, you have organic carbon from the rock, you have petrogenic organic carbon to think about. So the kind of final reflection really from me is a visit I made to a wildfire site in Northern California a few years ago, where I saw the results of a very large wildfire that had pretty much obliterated everything in its path. Every tree had vaporized into the air, and you started seeing great craters left, the chasms left by the fire itself. And on the surface, it looks devastating. But if you were to go down a meter, 2 meters, 3 meters, it was like nothing happened. And I think this is a interesting point to reflect on, because when we think about land management, agricultural management, we think about what we do to the land surface. How do we impact the whole soil profile? How can we make sure that the good things that we're doing are transported down the profile and helping that full depth that we should be protecting? And there are obviously going to be moments when the land surface is affected by drought and flood and wildfire, and the deep soil may be the refuge in these times of disturbance. So we think about soils at the land surface, but we really ought to do more work on soils at depth, just generally, to understand how they can be an area of resilience when we're combating problems. So I think in this lecture, I've talked about the importance of soils for different types of capital, those 5 capitals I mentioned. But whatever we want from our soil, we have to realize that soils are 3-dimensional bodies, and they have structure and a kind of dimension to them that we need to consider. And the lifespan of soil is dependent on both the processes taking place at the surface, the erosion of soil, and the formation of new soil at the bedrock. And the parent material is very much the foundation of where soils are from. But parent material is more than just future soil. It can act and function like a soil. It can store organic carbon, and it can release organic carbon also back into the soil. It's a dynamic zone, and we should be thinking about it much, much more. So I think with that, I've come to the end of my presentation, so I'll stop sharing and hand back to you.
Thank you so much, sir, for sharing such a deeply insightful and enriching session with us today. Now, if any participant has any question or doubts, they are welcome to unmute their mic to ask the question directly, or they can drop the same in the chat box. In the meantime, sir, I would request you to wait for a minute or so because majority of our participants actually prefer to write in the chat box. Thank you. Sir, there's a question from Mr. Ajay Sharma. First of all, he has thanked you for such an informative presentation. And his question is, considering India's diverse agroclimatic regions, how does variability in the bedrock soil transition influence long-term agriculture productivity and natural resource management?
It's a very good question, and thank you for the question, AJ. So what I would say is that there is a great variability, spatial variability of the bedrock soil transition in terms of the type of bedrock. So in some cases across India, there will be soils overlying soft bedrock where the weathering rates are very fast. Some bedrock will be harder, more consolidated, less susceptible to weathering, and that will create soils more slowly. So just on the face of it, we might understand how across India there's different rates of soil formation. And that basically then drives the thickness of the soil. So if you have erosion, which is removing the soil, in some parts of India, the formation rates might be able to keep those erosion rates okay. They will cancel them out and produce a soil just as fast as it's been eroded. And for some other soils, they won't produce soils as fast, and those soils will eventually erode. So really the big question is, we have to understand the rates at which soils are forming as well as the rates at which they're eroding across India and get that real spatial variability in. And that will help us understand the long-term productivity of agriculture and how we can manage those natural resources more effectively.
Thank you so much, sir. Participants, once again, if anyone has any questions, they can either unmute their mic or they can drop their question in the chat box. Sir, I think no one else has any question since you delivered it so beautifully and clearly.
Well, I'm not sure. Yes, thank you.
So I think we will conclude this session if no one else has any questions. So, sir, a heartfelt thank you to our esteemed speaker, Dr. Dan Evans, for sharing again such a deeply insightful and enriching session. Wait, we have a question now. Sir, Mr. Kanchan is asking, what is salinization? Please explain.
So salinization, and I know that this is a large problem across the region of India and other areas as well, is the process whereby in the water within a soil, the salts will accumulate. And typically what this means is that when soils are pulling water from often groundwater, the salts which are held within the water rise up to the surface. And over time, what you'll see is that the surface of the land and indeed the top 30 or so centimeters will hold lots of salt, and this will, I mean, some salt is fine, but too much of it will hinder a plant or a crop's ability to absorb water, and it will impact the crop yields. So this is a natural phenomenon, a natural process. It essentially happens because salts are dissolved into water, but if you have too much in the water, it will be pulled up to the surface, and you will see kind of a whitish, greyish surface at the land surface. You can see this film of salt, and this will hinder the ability for crops to flourish sustainably over time.
Thank you, sir. Many participants are actually requesting your presentation. So if it's possible, could you please share it? Our founder, Dr. Prakriti ma'am, will give her email to share on it.
Of course.
Yes,
And by the way, feel free to email me or to reach out to me on LinkedIn, or indeed any of those other platforms. I think you've got my details to share, but feel free to share, and I'm happy to receive further questions and comments later on.
Thank you so much, sir. Another question from Mr. Vivesh. What is the most promising emerging sensor or remote sensing technology that you think will revolutionize our ability to map and monitor the bedrock soil transition zone at scale?
Yes, a very exciting kind of question, because we're trying to find a technology that can see through the soil. And that's not very easy, of course, because in some cases we're talking about meters below the surface. So one of the things I'm working on at the moment is the application of synthetic aperture radar, which is the ability for a signal to be emitted, in this case from a drone, which then travels through the soil and is absorbed by the soil, but released back to the drone. And this can give us a sense of how deep the soils are and where that bedrock soil transition zone sits. It's not fantastic. Better to use some of those seismic instruments I talked about in the talk to get a more accurate depth understanding of where that transition zone is. But the problem with those seismic measurements is that you have to do many of them, hundreds of them, to get a real sense of spatial variability, whereas the UAV-based synthetic aperture radar, the SAR, creates a continuous map over a single field. So we hope that this UAV or drone-based synthetic aperture radar will help us map and help monitor the bedrock soil transition at some scale across the catchment.
Thank you so much, sir. And I believe that was our last question of this session. So we will conclude it. Sir, your perspectives today were not only highly informative and true, but they were truly inspiring. And we are sincerely grateful for the time, effort, and clarity you brought to this engagement. So before we conclude, I would like to extend a heartfelt invitation on behalf of the Agriculture Valley Research Foundation. If your time and commitment ever permits, it would be a great honor and privilege to welcome you to India, especially to the Indian Agriculture Research Institute, New Delhi. On behalf of the AWRF, I would also like to say that our doors will always be open to you. We're truly honored to host you for a lecture, workshop, or simply an opportunity to engage with our members, students, and researchers. We sincerely hope that someday your circumstances and your schedule will allow us the pleasure of welcoming you to India. Until then, please know that your presence with us today has been deeply valued, and we look forward to staying connected and exploring opportunities for future collaboration. We also extend our deepest gratitude to our respected founder and chairperson, Dr. Prakriti Srivastava, whose vision, constant encouragement, and unwavering dedication continue to guide and elevate the Krishi Navyug program. A special thanks to all our participants for their active engagement and enthusiasm, and to the entire organizing team for their seamless coordination behind the scenes. With this, we conclude today's session. Thank you once again, sir. Thank you, everyone, and have a wonderful evening ahead. With this, we come to an end to our session. Thank you.
Thank you.
Participants are free to leave the meeting now.